Worksheet 16b, superposition for the steel with the Y flange shape shown, and they give us the Young modulus, the area moment of inertia of the beam, and assume elastic loading, determine the midspan deflection for A. The second, determine the deflection at free end, and the last one is deflection at the free end for the cantilever and for the cantilever as well. So for here, for A, as you can see, go back to review the superposition, and then we go to the appendix. So process of determining load stress, in this case the loads, one at a time and add them together. And assumption, geometry not significantly alter, linear elastic, the problem gives us linear elastic, and use appendix B, which is same end condition, same load and same point of interest. Okay, so let's go to appendix D here and go back to the problem. They have a midspan deflection. That's the point of interest. For this case, is this point, midspan. What is deflection at that point? So we use superposition for the A. Let's work for the A. So what do we have? We have two types of load here. The first, distributed load, uniform distributed load, 2.5 kilonewton per meter throughout the beam, and then we have a concentrated load 9 kilonewton at the midspan. So with that, we can consider one at a time on this component. So the first one we have here, so with the pins and the roller and distributed load throughout of this span, and that is 2.5 kilonewton per meter. And then we have another concentrated load 9 kilonewton on that beam, and we have that load is also at the midspan 9 kilonewton. So the span for each beam, for the beam here at shown 15, so it's 30 meter, and that 30 meter. Use your common sense, and you can see the elastic curve, it will be bent down like that, and the let's call the deflection at the midspan for this point in the midpoint here, we call that is y1. And of course, similarly for the next beam, we also call the deflection at the midspan, which is interest, and that is y2. And you consider each of them, and we add them together, we can have the total deflection for both concentrated load and distributed load. So what do we have here? We have the total deflections of the combined load as shown. It equal to deflection due to the distributed load 2.5 kilonewton per meter at the midspan, and the deflection y2 due to the 9 kilonewton at the midspan. And from that we can use the table in appendix D, and must use exactly same finger. So for the first distributed load that we can use this table, okay, finger 6, and the maximum deflection, as you can see for this, for sure it will be at the midspan 1/2 L, and you can see that y max, and y max is -5 WL4 over 384 EI. So that is the first finger we have. The other is the 9 kilonewton, that is the finger 4 that we have, and that in the midspan maximum also at the midspan, and that also the point of interest that we have, because that the question at the deflection at the midspan, and the maximum deflection equal to -4 L cubed over 48 EI. So add these two in the third column, we will get the answer for finger 4 and finger 6. Everyone see that there? Yes? Okay, so let's go back here to have that down to appendix D. So we have y equal to negative 5 W L4 over 384 EI negative PL3 over 48 EI. And that, I just make sure you remember it later, that is appendix D. Okay, appendix D. So that from that appendix D, we can plug in the number. So we can get here negative 5 W 2.5 30 with the L power 4 384 gigapascal. So we change it to Pascal. So we have kilonewton, so kilopascal. So it will be 200 times 10 power 6 kilopascal. And then 410 times 10 negative 6 to change from millimeter to meter power 4 from the I-axis there. So that is here. And then we have another component, it P, which is 9 kilonewton. So we have plus the negative 9 L cubed. So it will be 30 over 48 EI to kilopascal, because the load is kilonewton. So we have that, and change the to meter again. So we have that for 10 negative 6 from for 10 power 6 millimeter 4 to meter 4. So from that one we have Y equal to 0.384 meter, and that the answer going down, right? It's negative number, as you can see, negative. If we change the direction, we can say that is going down. So then you don't put the negative here. You don't put the negative because you already magnitude the direction. Everyone got that one. And as you can see here, the equation already have negative. So what we plug in the load, even the load going down is negative, but I put, as you can see, 2.5 positive, and based on that equation. And P 9 kilonewton is even going down, but they already built in the negative in that equation deflection, so you don't have to double another negative so that it become a positive. It going up, the deflection going up, which not make sense, because the total deflection of that one here, it will be something like that. It will be like from here to here and go to 0 again, and you can see that the Y max here is Y max, and that Y is the question asked, and that is going down. So it, as you can see, common sense in there. So next video we'll go to B and then C.